Hello and welcome to Lecture 18, our second lecture in our continuing study of optics. Our first lecture was about double slit interference. And to continue that idea, we're still going to be talking about interference, just a different type, called thin film interference. And really, all these ideas about interference is just getting two waves in the same place at the same time, so they constructively interfere when they're lined up on top of each other like this, or maybe they destructively interfere when they're exactly 1/2 wavelength out of phase, like that. Okay, but now we're doing it with thin films. So our objectives are to understand how interference can occur when light reflects from two surfaces of a thin film, like the top and the bottom surface, okay? The upper and the lower surfaces. Now, we also want to conceptualize that this type of interference requires a thin film. Why not a thick film, in other words? Because otherwise, the refraction will mean that the reflected rays are not close enough to each other to actually interfere, okay? Now, we'll talk more about refraction later, but the point is, all these ideas only work for thin films. Now, thin means how thin? Well, it depends on the light, okay? So let's take a look at our key terms. So, first, defining what a thin film is. It's a transparent layer. It can be transparent to visible light. It could be transparent to some other type of light that is not in the visible spectrum. The point is it's transparent, okay? It has a thickness defined as T, it's the letter we use for it. T does not represent time here, it's T for thickness, that is on the order of the wavelength of the light. Well, there we go. And when I say order, I don't mean equal, I mean within a factor of 10 of the wavelength of the light, okay? Now, thin films, in practice, can cause interference because the reflected rays from the top and bottom of the film are close enough to superimpose, they're on top of each other, and these reflected rays may have a phase difference due to path length differences and something called the reflective phase shift. Okay, so we have to define those terms, path length difference and reflective phase shift. But first, let's just talk about these two rays, the ones from the top and the bottom. I have an example here. Here are our two reflected rays. Now there's three rays, really four, shown in this figure, but these are the two that are actually going to interfere with each other, the two that are shown in pink. Now I say there's four rays because there's also this initial green ray, which we would call the incident ray, right? And I'm saying the word ray a lot. Ray is a term here, it's referring to the path, but to be fair, I should be using the word wave because we do care about the wave nature, okay? And so reflected rays, this term, I did write it here and it's not the wrong term, but here we are focusing on waves. Okay, but this would be the incident here. So incident, it's the incoming, and that term will come up again. And then we also have a transmitted wave or ray, all right, transmitted, because it's actually going through the transparent material. Those are the total four rays. One incident, one transmitted, and two reflected. The reason there are two reflected rays is we get a reflected ray every time we change materials. So when we go from the air to the film, that's the thin film, that's a change in material, thus a reflected ray. When we go from the film to whatever's underneath it, in this case, some other substance, that again is a material change, so there's a second reflected ray. So those are our two ones, our two reflected rays, or in the language of this lecture, waves. Okay, and there is our thickness, T, all right? Now in this case, it's equal to exactly 1 lambda. Now, there might be interference, right? In this case, is it constructive or destructive? If you look at this figure, do you see constructive or destructive interference? Right? Consider that, okay? That's one of the ideas we'll be coming back to again and again, certainly in the examples to come in just a few minutes. But other than the idea of a path length difference, there's also this reflected phase shift. And what is the reflected phase shift? Well, it's a rule. We're not going to get into the underlying physics of it, but it's a rule that we can obey, all right? And it tells it, and it applies, first of all, to all waves, not just light, all right? But for light, it's specifically going to be in the context of this term, the refractive index, which I introduced in lecture 17. So far, the refractive index tells us that the wavelength of light changes when light slows down effectively when it passes through a transparent material. Now we know in a vacuum, light always travels at a fixed speed, but it effectively travels slower through when it transmits through transparent materials like water or glass or a gas, right? But although gases will have very, very low reflective indexes, very close to 1, which is the reflective index of a vacuum. It's exactly 1. Okay, but point being is that's a term we looked at. It changes the wavelength of the light. Okay, so how does that apply then to this situation? Well, the phase difference between an incident wave and a reflected wave is always pi radians or 180 degrees if the reflection occurs from a lower, all right? So from a lower to a higher index of refraction, because the subscript 1 here denotes the initial index of refraction. That's where the light is coming from. And here the subscript of 2 denotes the next material, like the film, the thing that comes afterwards, okay? Where maybe that's what the light is reflecting off of, and maybe it's also partially transmitting through it. But the point is that the reflection part will have that phase change as long as the refractive index goes up, from lower to higher, okay? For example, if the initial refractive index, the initial material through which the light is traveling, is air, which has that refractive index that's the same as a vacuum, essentially, close enough, it's just 1, okay? Well, then this light then passes from air into glass. That means the next refractive index, N2, is that of glass, which is, of course, greater than 1. It's 1.4, okay? And the idea is that, I mentioned the wavelength, because the wavelength of light in glass is just going to be the wavelength in a vacuum, which we'll call the base wavelength, divided by the refractive index, all right? In this case, the refractive index of glass, okay? So it would be divided by 1.4, it'd be that much smaller, okay? All right, so that would be an idea where there is a reflective phase change, or a case, because we're going from lower to higher, okay? Indeed, that's what I showed in the picture. So let's pay attention to that, okay? Because so far, the path length difference, it was here, I didn't call too much attention to it, but the path length difference was what? Well, the first reflected ray, went up this way, okay, initially, right, immediately from the upper surface of the film. But then this reflected ray that was reflected off the bottom of the film, it had to travel through the film, so it had 1 extra wavelength going down, and then it had to travel back up out of the film. So then its path length difference, delta R, the same term that we used for path length difference in lecture 17, well, delta R would just be equal to 2 lambda, because I said that the thickness is just lambda, just by, that's just a choice. It just happens to be equal to the wavelength, okay? All right, and so that would mean that the waves are in phase, because the difference is not a multiple of a half wavelength. They're not out of phase. They're basically remaining in phase. We just added another full wave, but another full wave means you're still synced up. You're still in phase, okay? Now, but there's still reflective phase changes. It's still there. It's just that it doesn't actually seem to matter here. And where do we see the reflective phase changes? Well, we see it at both the top and the bottom of the film, because we went from 1 to 1.3, so our refractive index went up, and then we went from 1.3 to 1.5, our refractive index went up again. So it means we had 2 reflective phase changes in addition to the path length difference. Okay, well, here it is. If we look at the incident wave, the very first one at the top of the film, the reflected wave has the opposite form. It's like it was flipped upside down, because you can see that the wave came in leading on a trough, like a low point, lower than the equilibrium line. But when it got reflected, it reflected as a crest above the equilibrium line. It got flipped upside down. That's a phase change of pi radians, or 180 degrees. We could also say that's a phase change of 1/2 a wavelength, okay? And that's what we see. All right, so we see the same thing at the bottom, the same exact reflective index. Well, it's the refractive index, it's the reflected phase shift. But what's interesting is, since it happened at both the top and the bottom, it didn't matter. The path length difference that kept things in phase still was the same, right? So the fact that there's 2 of them, they kind of cancel each other out, these 2 reflective phase changes. But there's not always 2. Think if we went from air to film back to air instead, all right? Well, in that case, there'd only be one. Oh, that would change things, wouldn't it? And that's what we're going to see in the examples. But first, let's take a look at a couple other related expressions about the reflective phase shift, and then right on to our key formulas. Okay, so the phase difference between incident and reflected waves is 0, so nothing, when you go from higher to lower, right? And there's just none. The reflection is unchanged. The wave would have the same form. Okay. Now, what's interesting here, and this is you may not remember waves on strings as much, or other types of waves, way back to sound waves. But I do want to make that connection because ideas that apply to one wave apply in many cases to other types of waves, and that's the case here because this is the same idea as standing waves on strings having nodes at fixed ends, because the fixed ends act like an increase in refractive index in an abstract way, and that means that the reflection is out of phase by exactly half a wavelength or pi radians, and that means there's cancellation, and a node is a point of constant cancellation because of that reflective phase change. So it's the same idea. Okay, so key formulas. Let's define our variables. So 2t, all right, that's twice the thickness. That's always equal to the path length difference every time, because the wave that gets reflected off the bottom of the film has to travel into the film and then back out of it. So the path length difference is always twice the thickness. Okay, all right. Then the film thickness, of course, is just t, right, measured in meters. We have m. This is the same idea that we saw in interference patterns from double slit interference. M is a counting mechanism because we would have lots of possible thicknesses that could apply to cancellation. There's not just one, right? There is a series of them, and therefore we have an order of the interference, and so m is an integer, okay? And m can be 0, 1, 2, and so on, okay? Then, of course, we have lambda, which is the wavelength, okay? For visible light, somewhere in the hundreds of nanometers. Well, 500, 400 nanometers, okay? Now, turns out, let's back up one sec. Turns out these equations, right, we look at them, you might say, oh, well, this equation applies to constructive interference because it's full wavelengths, and this equation applies to destructive interference because it's half wavelengths. And that because these look like similar equations to maybe the small angle approximation of double slit interference. And it's many of the same ideas. But you'd be wrong to simply say that this one is constructive and this one is destructive. Because, as I just showed you a second ago, there's more to it. In fact, these equations serve double purpose. They can mean one thing in one context and another in another, okay? And that's the one thing you really have to understand about this system, okay? So if we look, we see that this equation here applies to constructive interference when there are 0 or 2 reflective phase shifts. Here I just call them phase shifts, but I mean reflective phase shifts. But then the same formula applies to destructive interference when there's just one phase change. All right, one phase shift. Interesting, okay? And this one does apply to destructive interference when there's 0 or 2, okay? And the example we're looking at, the air to glass to some other substance, well, that was the 2 case, okay? So that would be this. But on the other hand, if there's only one phase change, then this same formula applies to constructive interference. So what you really need to know is all the refractive indexes of your different materials, so you can, first of all, know whether there are 0 or 2 phase shifts or 1, because then you know what formula to use, okay? Or what your formula means. All right, so let's get right onto our practice, starting with a concept question, all right? All right, so we're going to start with a thin soap bubble line, because soap is a good example of this. Soap stretches really thin, especially in a bubble. And so it has those properties where it has a thickness that's on the order of visible light. And another common one is oil on water, because it spreads out really thin, just, thin layer molecules, and, on this few hundred nanometers, and then maybe, a fraction of a micron. And then, that's the idea, all right, or a couple microns. All right. So our soap bubble, here it is, right? This is like the edge of a big spherical soap bubble of some sort. All right. Now we have air on one side. We've got the soap, and then we've got air again. So we go from lower to higher, but then back to lower. How many phase shifts is that? You gotta think about it, okay? Of course, I'll tell you in just a moment. These are going to be our 2 interfering waves, okay, reflected from the first layer, the upper layer of the soap, and from the bottom layer of the soap. And we were asked, what is the minimum thickness? It sounds like maybe this is more of a numerical problem than a concept question. But it turns out it actually really is a concept question because the answer is kind of interesting, okay? So, we're going to say, well, you're going to see. So how many reflective phase changes are in this case? Well, it turns out that the thickness we're going to find is about 0. We need the thickness to actually be dramatically less than the wavelength of the light. So to not be on the order of the wavelength of light, to be so much thinner that these two are essentially on top of each other. Okay, interesting. And the reason for that is because there's only one phase change, right? Just at the air to soap interface, okay? And that means there's just that one shift, okay? Thus, m equals 0 means that we have 2t, because think about what we want for destructive interference. Now, this is our equation for destructive interference. And we want the minimum thickness. Well, the minimum thickness is always m equals 0, right? Whether that's a minimum thickness that's for construction of an interference or constructive interference, or whether that's a minimum thickness for destructive interference. Your minimum always is m equals 0. Well, here, when you plug in m equals 0, look what happens. It's kind of weird, right? Your t ends up being 0 because you got to solve for t, and anything times 0 is 0. So your minimum thickness is actually 0 meters. What? That's really interesting. What does that mean? This tells us that actually a very thin thickness, t much, much less than the wavelength, would create destructive interference. Because you essentially need there to be no path length difference. You need the only thing to matter is the reflective part of the interference. Because look, you got the one phase change here, but here there isn't a phase change, right? And since there's no path length difference, the case where there isn't a phase change is basically the same as the incoming wave. So now you have these two waves that cancel out. All right, it's precisely because the path length difference is negligible. Right? It's a very interesting effect. It's like you need the thin film in order to have the two reflective phase changes, but you're also almost ignoring the thin film because you're saying, oh, it's so thin that there's actually no path length difference. But in practicality, it is a fairly realistic situation as long as the thickness is much, much shorter than the wavelength. Okay. All right, so we're going to do another one that actually is going to run some numbers. Example 1. Red light is viewed through a thin vertical soap film. At the third dark area shown, the thickness of the film in terms of the wavelength within the film is what? All right, take the wavelength of red light to be 650 nanometers and the index of refraction of soap to be 1.2. We're going to assume the large red area on top is the minimum thickness for constructive interference. Because the idea is that the soap is running down. This is what happens when you're blowing bubbles and you hold the thing that holds a suspended bubble. It gets thicker at the bottom because gravity is pulling that the liquid down, which is the soap. Okay. All right. So we have a single phase change. We already know that from the previous question, air to soap. Okay, because there's air on the back side of this, of course. All right. So the large red area is constructive interference. Okay, constructive interference is this formula here. All right. We know that from the table on the previous page of the key formulas. All right, notice that I wrote lambda prime. I'm going to come back to what that means. You might remember from the previous lecture. All right, so then when we solve for that thickness, it's 1/4 of lambda, or lambda prime. All right, that's an m of 0 because it's a minimum after all for constructive. The dark area is destructive, obviously. This is the first dark area. Now the first dark area, we set it up. There would be this equation, again, m of 0. All right, but when we plug in, well, actually here, it's not, this is the first dark area. I want to make this clear. Here we're actually plugging in a m of 1, not 0, all right? Right there, m of 1. You might be like, wait, but it's the first dark area. Yes, but it's the first dark area where there is destructive interference, but it must be thicker than the first area where there's constructive interference. And what do we already know is the actual first thickness for destructive interference? Something that's way thinner than lambda. So that means that the soap just never got that thin. Right? There is no region, maybe it would break. There would be if we allowed the soap to continue to get thinner, then we would lead with a dark region. But since the uppermost region, the thinnest area is red, that means that this area is in fact not really the first in terms of the actual order of the interference. It's just the first in terms of this physical soap suspension, okay? All right, hopefully that makes sense. Now we're gonna skip over second because we see the trend, and we're gonna go into the third dark area. Again, formula for destructive interference. What's our m this time? Well, it's going to be 3, all right? And now normally the third would be 2 because it's 0, 1, 2. But this is again third because we started with 1, all right? And then we plug in our numbers because we did after all have numbers. And I'll finally now go back to what I hinted at, or said I would say in a minute, which is what is lambda prime? Lambda prime is the wavelength within the film, which is not the same as the wavelength. Because when you're given the wavelength, that's the wavelength in a vacuum. right? Unless you're explicitly told otherwise. So that means we need to take the wavelength vacuum and divide by the index of refraction of the SOAP. So it's lambda over n, all right? So that's all I've done. I got the 3 halves, which just came from the order of the dark area, and plug in our actual wavelength and the index of refraction, and we find out that the thickness down there is 813 nanometers, right? Still really thin. Okay, let's do another concept question. A film with thickness T gives constructive interference for light with a wavelength in the film. Okay, so here we're not worrying about dividing by the refractive indexes. This is just the wavelength within the film. It's always taken care of. How much thicker would the film need to be in order to give destructive interference? Okay, so what do I mean here? Well, let's add some details to the figure. So there are two initial waves, all right, 2 original reflected waves. And we know that they're giving constructive interference, which means they got to be in phase. Now, I'm just going to assume that they're in phase in such a way that there are no reflective phase changes. Okay, so you can see here that the waves are keeping their same form, so there's 0 in terms of the reflective phase changes. And the thickness, as you can tell, is, well, look, exactly 1 wavelength. Now, we can make any choice because the principle would hold for any case. This is just what I kind of chose to illustrate the idea. Now we're going to be making the film thicker. So we're going to be taking a light blue and making it larger effectively. So there's some added thickness, delta T. So that means that now our new reflected wave would need to look like this, because the new reflected wave, effectively replacing this one here, all right, because it's the one reflecting from the back, it's now reflecting from a back that's further away. And it's further away in such a case that now how much wave fits in there? Not 2 full wavelengths, one going in, one coming out, but instead 1.5 going in, and then 1.5 coming out, which of course is 1.5 plus 1.5 or 3 wavelengths, okay? Or rather, it's 1.25. It's important. It's 1.25, not 1.5. And so we have 1.25 coming in, and then 1.25 coming back out, because again, this is a quarter wave, all right, 1/4 of a wavelength. And so 1.25 plus 1.25 is 2.5, and 2.5 means that we have a half wavelength phase difference. In other words, we got a trough where there was an incoming crest. These cancel out. That's destructive interference. Destructive interference, totally destructive. Okay, so there it is. There's the picture. And again, it applied to this case of 0 phase changes. It would apply to any case. Okay, and what do we know? Well, we look at it, we can tell. I already gave it away. What is the additional thickness? A quarter wavelength. So we see the change in thickness of 1/4 wavelength results in destructive interference. If you want to make it destructive and it was constructive, and you want to change anything about the system, don't change the refractive indexes or the wavelength or anything, just make your material 1/4 thicker, and it will change the effect every time. It'll go from constructive to destructive. Okay, let's do another example. This is another common type of problem. Now, by the way, you might have noticed or thought I skipped over the types, or I always talk about the types of problems in my lectures. That's because there's only one type of problem, just problems that involve thin film. There's not enough variation between them. So 2 very flat glass plates that have a certain length, they're 26.5 centimeters long, are in contact at one end and separated by this separation distance at the other end. It's like a wedge shape. The space between them, I'll draw a picture, between the plates is occupied by oil with an index of refraction of 1.22. The refractive index of the glass itself is 1.51. All right. The plates are illuminated at normal indices with monochromatic light, and fringes are observed. A pattern of fringes, in fact. When the monochromatic light has a wavelength of 555 nanometers, there we go, there's our lambda, how many bright fringes are visible in the pattern? So how many fit on the wedge? What is the spacing between the fringes? So here's the picture, right? It's the glass with its index of refraction, the idea that it touches at one end, but there's a separation at the other. This is not at all drawn to scale, right? There's actually that wedge would be tiny because it's just on the order of 10 to the negative 6, whereas this is centimeters, all right? And then we've got the length, that's just the length of the glass, and then the wedge height, right? And then I also have X and T. T is the thickness that shows up in all the formulas. X we haven't seen before, so we'll see why we would need that here, okay? So we want to consider this ratio, because whatever is the overall triangle, the dimensions we're given in the problem, that triangle, right, a right triangle, has to be similar, have equal proportions of some distance measured from this edge and the thickness at that point. So X is a variable, a measured distance from the left edge, okay? And so these are similar triangles, same ratio. So that means then we can solve for the thickness, all right? And it's X times H over L. We don't know what X is, but we know H over L. okay? And our thickness for bright fringes is, let's think about it, all right? So this is going to be the formula we're going to use, all right? Now, why is that for bright, for constructive interference? Well, because there's a single reflective phase shift, okay? There's only one. You see, this always comes up, and all these problems, you always got to make sure, because that's actually the only reason we care about the index of refraction of the glass. We otherwise don't use that number. We only use it to know that initially we're going from higher to lower, so there's no reflective phase change that time. But then on the bottom of the oil, there is a reflective phase change because we go from lower to higher, okay? Now, I say that we only use the index of refraction of the glass for that purpose. The number is never calculated. But I didn't say that for the oil because the index of refraction for the oil is necessary because it's going to set our wavelength. Because we were given a wavelength in a vacuum, but we need to account for the adjusted wavelength within the material, all right? Now, it's only ever within the film. And here, the film is the oil. How do you know that's the film? Because the film is just always the thing in the middle. It's the thing sandwiched by the other two materials, even if those other two materials are air. Right? Still the thing that's sandwiched in the middle. All right, so we've cleared up that this is the formula that we want to use for bright fringes, the constructive interference formula. All right, and as I point out, this is our corrected wavelength, if you will. All right, so let's find out. In oil, the wavelength of this particular monochromatic light is 463 nanometers, unlike what it is in a vacuum. All right, and now we're going to find the largest M value, okay? And that's going to come from setting the thickness equal to H. Okay, because when we do that, we were to say, okay, well, that means we just need to find out how many fit along this length. See how that's effectively just going to cancel out H, all right? Okay, so there we go. Well, I guess it would if we plugged it in here, but here we're actually going to plug it in this formula here, and we know what H is, we were given it, okay? And now, what are we going to solve for? We're just going to solve for M. Because think of what we asked. We're asked, when the monochromatic light has a wavelength, how many fit? Well, if I can find out the order of this last one, then I know there had to be that many all the way down to M equals 0 at the far left end. So all I need to find is whatever the last one is, okay? So we're just going to solve for M, just solve it from this algebraic expression, isolate it, right? So I end up with this, all right? I'll plug in my numbers, and I find that 73 bright fringes fit, okay? Because that's the last order. We go from 0 to the end, okay? All right, good. Now, we're also asked, what is the spacing between the fringes? Well, now that we know there's 73 of them, can we just divide L by 73? Well, yeah, sure we can, all right? So we could do M over L, which gives us how many fringes there are per meter. So that's interesting, right? I just figured I'd add that in. But then we were asked for the spacing between them. Well, of course, that's the reciprocal, or just L over M, and it's 3.6, right? So every fringe is spaced 3.6 millimeters apart, right? Because there's 73 of them. And they just be all on there. You see a pattern, a evenly spaced pattern running all the way up this glass. And this is something that commonly happens. Scientists notice it when they're working with slides. You can see that actually everyday effect of light. Okay, so you can see that counting phase shifts, the reflective phase shifts, is so necessary. So let's do some quick practice. I want you to make sure you can do this yourself, right? So pause the video if you need to, but you want to count the number of pi, or 180 degree reflective phase changes. This is the only type of reflective phase change there is. I'm just reminding you that it's pi, all right, that occur in each of the following cases. Okay, so we're good. All right, so let's run through this. So the first one, well, from n of this n2 is less than n1, and n3 is less than n2. So that means there's 0 and 0, or there's none and none. So that means the total number is 0. There's no reflective phase changes. All right, what about in case B? Well, there is one when we go from 1 to 2, all right, because 2 is bigger than 1, so we have one reflective phase change, but not the second time, the second material change. So that means we have 1. And look, hey, look, here we go from 1.2 to 1.5 to 1.75. So sure enough, we go from lower to higher still. So we have 2 reflective phase changes. All right. Okay, let's do our last example, example 3. All right, so a thin film of oil, I said one of the other common situations, with an index of refraction of 1.5, and with a varying thickness, floats on water with an index of refraction of 1.33. When the oil is illuminated from above with white sunlight, the colors appear in the oil film as shown below. In air, the wavelength of light is 580 nanometers, okay? Which means in a vacuum, effectively. So what is the oil's thickness T at point B? All right, so again, there's always a bit of a kind of interpretation with these problems, right? We have to interpret what it means that it's dark over here, and then we have this pattern, blue, yellow, red, blue, yellow, okay? Well, first of all, we want to find the thickness T that will lead to constructive interference. So that's the first interpretation. The fact that this is yellow means that yellow light is being constructively interfered for this particular thickness. This thickness doesn't match up for constructive interference for the blue and red parts of the rainbow. And so it would appear yellow because that's the light that is getting, amplified, right? Really the only light that's surviving, okay? So we pick up yellow, all right? And how many reflective phase changes? Well, there's one, all right? So that means constructive interference would be this formula right here. Very good. And we want constructive because we're looking for it, all right? So we know, and now we know where we want to use, the yellow wavelength, all right? Yellow lambda. Furthermore, last bullet point, the thickness shown must have an M of 1. So again, reasoning out, why is it 1? Why is it the first order? Since the dark region corresponds to thicknesses much less than lambda. So, okay, so in other words, this is M equals 0, all right, for destruction. And then that means that we have this blue here is M equals 0. This yellow is M equals 0 for constructive interference. So this one is truly the smallest constructive interference case. So that means by the time we get to this one, this second yellow band, that's M equals 1, okay? Oh, and here I wrote M, I just realized I wrote M equals 0 for dark, but this is M equals 0 for destructive. It's the far end, okay? Because we're leading with that, well, we're leading with the fact that we have destructive interference. It's unlike the soap bubble where the thinnest part was constructive, even though it could have been thinner still. Here, this is as thin as it gets, okay? All right, so good, that sets our order, M equals 1. And then it's a matter of plugging in, all right? So we're gonna go ahead and set this up. All right, this is gonna be lambda in the oil. Lambda in the oil is the wavelength in air divided by the index of refraction of the oil, so same thing there, substitution, okay? And then we'll plug in our numbers, all right? So we got a half of a half after we solve for T, and we get 290 nanometers. That's how thick our oil is. They get the second band. When you look at oil, you actually see many, many different bands in complicated forms because the thickness varies kind of randomly. But this is the underlying idea, the underlying physics. It's all about reflective phase changes and path length differences leading to interference of overlapping waves. Okay? All right, so I hope this lecture has been interesting and informative. Thank you so much for watching.